Alright, welcome everybody to the Chapter 9 lecture video. We are going to be talking about estimating a population proportion, and then in the next section we're going to learn how to estimate the population mean. So two different things going on. Remember the proportion is the p hat, that's for a sample, and the mean is the average. So we're going to see the differences, but they work the same way. It pretty much works the same way. We're going to learn how to construct a confidence interval. And that confidence interval is what we'll use to estimate the true population proportion. Because we don't have the population proportion, but we want to kind of have a general idea of what it is. And that's good enough. So let's get into it, and we'll just kind of go over the book real quick, and then after we go over the book we will just solve a bunch of problems. But let's just kind of get a sense of what the book is really talking about. And the very first part is, in order to build a confidence interval, is you have to get your point estimate. And your point estimate is pretty straightforward. The point estimate is p hat, which is your x over your n. X is the number of successes, if you want to call it, and n is the sample size. So that's pretty straightforward, and that's your p hat, and p hat is going to be in the middle of the confidence interval. So here's an example on getting the point estimate. Okay, this is very simple and simplistic. Here it says the Gallup organization conducted a poll in which a random sample of 1,016 Americans 18 or older were asked, do you consider the amount of federal income tax you have to pay is fair? And then of the 1,016 adults, 558 said yes. So our job is to figure out the point estimate. And it's just really easy. It's just going to be the percentage of those 18 and older, Americans 18 and older, that said yes. So that's 550 divided by 1016. So it's literally the point estimate of the population proportion is going to be 558 over 116. We get 0.54, which is 54.9%. All right. So what we've done is we've got a sample, and that sample was an SRS, a simple random sample. So it was a good sample. Only 1,000, that's small compared to the number of Americans in America. I mean, that's 18 and older, right? There's millions. We got a nice tiny little sample. But the point estimate turned out to be 54.9%. So that's what we're going to use to estimate the true population proportion. Just because we cannot survey every American 18 years old and older. So we'll use the population proportion, we'll use our point estimate to estimate the population proportion. So that's how it's done, really easy. And then the next part is we need to construct a confidence interval around the point estimate, because we know that there's going to be error in our point estimate. So we have to decide on how big or how wide we want our interval to be. And so that gets into the confidence interval and the level of confidence. All right, the level of the confidence, if we want to be very, very confident, like 95% confident, then we're going to have to make our interval wider, cast a bigger net. A low confidence interval means our low confidence will be a smaller interval. So it's pretty basic. And then this is key. Point estimate is equal to plus or minus the margin of error. It's pretty straightforward. And then the question becomes, okay, we know how to get the point estimate, but how do we calculate the margin of error? Because this is what a confidence interval looks like. This is one of the forms. You can write it as an interval. You can write it like this. You can write it in a lot of different ways. So the hard part is calculating the margin of error. The point estimate is the easy part. So you need a couple of things in order to calculate the margin of error. And they get into it here. It says, all right, why does the level of confidence represent the expected proportion of intervals? We're going to get into that. And then how is the margin of error determined? So the first thing we need to do is there's some like requirements, The shape of the distribution of all possible sample proportions is approximately normal, provided this is true, and the sample size is no more than 5% of the population size. The next part, the mean of the distributions of the sample proportion equals the proportion, we know that, and also the standard deviation of the distribution of the sample proportions is going to be equal to this. And so there's one more other fact too. We have to actually calculate the critical value. We have to multiply this by the critical value. And that has to do with our confidence level that we set. So we're gonna get into that as well. All right, so let's get to our formula. And this is the formula. It is P minus the critical value, Z alpha over 2 times the square root of P times 1 minus P over N. This is our lower interval, and this is our upper interval, and our P hat is in the middle. Our point estimate is in the middle. So, and I'm going to annotate right here, this piece is the margin of error. So I'm going to show how we calculate this out by hand. First thing you got to do is you got to figure out what Z sub alpha over 2 is equal to. And then once you figure that out, then you have to figure out what this is equal to, the square root of P times 1 minus P, which is really Q, all over N. Next, you got to figure out what that equals as well. And once you know what these two are equal, you multiply them together. And you add it to your point estimate. You subtract it from your point estimate. And that's how you get a confidence interval. So that other, let me see here. Right here is, again, this is some good stuff. This is how you would calculate it, okay? So we're gonna do a problem like this. And I've lectured on this. You can check out the lecture videos. I went over this. But it's good for us to just, if you hadn't seen that, it's good for us to just look at this video, because I'm kind of going over it in a more customizable way. It's not so generic. All right, and what's cool about getting the critical value, some critical values, like the really popular ones, they're well known. So the critical value is like the z-score, and I'm going to show you how to calculate that. But keep in mind that the critical value has to be positive. It's the right side, the right tail. But sometimes they'll give us a confidence level that's not so common. That's the hard part. Now, you can't just use table 1. You can only use table 1 if the confidence level is 90%, 95, or 99. But if they give you a confidence level like 89% or 91 or 93, then you have to calculate the critical value on your own. And I'm sure we'll run into a problem like that tonight. So let's just jump into it and start to calculate it. And again, we're going to do it by hand, and then we'll do it by technology. Our calculator and StatCrunch. All right. So yeah. Let's jump into those problems just to get a feel for what the problems are like. In fact, let me go into our stat lab. And let's go to assignments. And let's go to chapter 9.1. You're really going to like solving these using technology. Everything we do from this point on can be done using technology. The thing is though, we do it by hand first, because you have to know the inner workings of it, and then after you do it by hand a bunch of times, then we show you the easier way. So, and this is being recorded. It should be. Oh yeah, we are definitely recording. So question 1. They want us to do some matching. So match point estimate, confidence interval with its definition. All right. Well, point estimate, we already know that's just the value of the statistic that estimates the value of the parameter. So that's going to go right there. All right, this is a little tricky. Let's see. It has to be highlighted and then you let go. You have to drag and drop. A range of numbers based on a point estimate of an unknown parameter. Confidence interval. The expected proportion of intervals that contain the parameter if a large number of different samples is obtained. Level of confidence. And finally, what determines the width of the confidence interval? That is the margin of error. Yes. Yes. We got it. No, I knew it was going to be right. And this is good info, right? This is really good info. Like, this is where, like, you could just copy this somewhere and put it. I mean, this gives you the definitions of each one right there. It's not so bad. Not so bad. Okay, here's practice. Compute the critical value z sub alpha over 2 that corresponds to an 81% level of confidence. See, this is not a nice number. If it was common, like 90, 95, or 99, then we could just pull up the table and it will tell us what it is. But this is not common. So here's how you would do it, okay? This is really important that you understand this. So if I do something that's confusing, stop me and I can explain it further, okay? So the first thing we have to do is draw out what it means to be 81% confidence. What does this mean? And it will make sense to you once I draw it. So I'm going to draw out a normal bell-shaped curve, right? It's not that great of a hump um, of a bell shape. But what 81% level of confidence means is that we have the inner 81%. It's not 80, it's not 81% to the left. It's not the upper 81%. It's the inner 81%. Okay? So here's where it starts to get advanced. That means since it's the inner 81%, that means that these two make up 19%. Now, the reason why I got 19% is because the whole thing is 100. So that means that half of 19% is 9.5%. And this is another 9.5%. And so now get this. We're looking for the z-score that the right one, it has to be positive. There's the negative one. They're the same. It's just one's going to be negative, one's going to be positive. We're looking for the z-score that separates the top 9.5% from the rest. And that's what z sub alpha over 2 is going to be equal to, this z-score. Now, when we have the area and we don't know the z-score, we have to use inverse norm. Inverse norm is the one to use when we need to find the critical value. Now, there's a couple of ways we can do this. We can do, all right, and by the way, this is the standard normal distribution. So the mean is 0, the standard deviation is 1. I mean, we're literally talking about the standard normal distribution. That's what we use. So we can do this two ways. We can say it's inverse norm of 0.095, 0, 1 to the right if you have a TI-84 or higher. It will give you the option to calculate area to the right. Or we could just, if you don't have that ability, you can just do it to the left. But it's going to be the area to the left, which is 81 plus 9.5, which is 90.5. .5, 0, 1. And that will give us the critical value. And now it's time to whip out the calculator. And then move it over here so we can actually see it. This. I'm going to do second distribute. Inverse norm is number 3 on my calculator. And I'm going to put in 0.095, but I'm actually going to put in 0 and 1 and then area to the right. And we got 1.31. And now what I'm thinking is this should be the same as inverse norm of 0.9005, period. It has to be 1.31. We got it twice. It's the area to the left. It is the area to the left. So from here, the area to the left is 81% plus 9.5. That's 90.5 together. Oh, 9.5%. 0.095, yes, 0.095 is really 9.5%. And we got it right. All right, let's move on. Um, so it says in a survey of 2,025 adults, it's almost like the year, in a certain country conducted during a period of economic uncertainty, 55% thought that wages paid to workers in industry were too low. The margin of error was 3% points with 95% confidence. For parts A through D below, which represent a reasonable interpretation of the survey results, for those that are not reasonable, explain the flaw. We are 95% confident 55% of adults in the country during the period of economic uncertainty felt wages paid to workers in industry were too low. No, it's flawed. It has to give a level of confidence of vary based on the margin of error. It would have been better if we said between 52 and 58%. We are 95% confidence that between 52 and 58% adults in the country during that month. That would have been better. So it provides no interval um, for what we needed it to provide. Here, this seems flawed. It indicates that the level of confidence is varying. No, the level of confidence is stuck at 95%. Who did we lose? Okay, Diesel took off. Is the interpretation reasonable? This looks good. This looks reasonable. Oh, there's one more. In 95% of samples of adults in the country during the no, it's flawed because the interpretation, this should be part C. The interpretation suggests that this interval is the standard, and you can't just say that 95% of samples, we are 95% confident. So let's make sure that that's good. Okay. Now we get to move on. Let's keep going. Let's actually do one where we actually have to calculate the confidence interval. This is all conceptual. Yeah, this is all concept. Well, so there's like no question. So did I cut some of the questions where you're supposed to calculate the confidence interval? It seems like there was no practice. Um, yeah, there's. Let me see. Oh yeah, there's another question about determining sample size. Yeah, this is a good question as well. I think we might have pulled those. Let's look at some practice problems anyway. So here's some practice. Construct a confidence interval of the population proportion at the given level of confidence. And 90% is actually a common confidence, so we could find z sub alpha over 2 using the table. We don't have to recalculate it. This is a common one. 99% is common and 95% is common. 98, you have to figure it out. And our x is 30, our n is 150, so that's just great. Um, Here's some more practice. Determine the critical value that corresponds to this. Okay, so yeah, we'll do one of these and then we'll move on and we'll take this one. And what I'll do is demonstrate how to actually get the confidence interval using our calculator. And then our StatCrunch as well. How about that? We don't necessarily have to do this one by hand. And our job here is to find confidence interval in 3 ways. First, the TI is the instrument. So here we go. I'm going to clear out my calculator. And what we're going to do is go to Stat. Go over to Test, because that's what we're going to be doing. We're actually conducting a test. A statistical test to estimate the population proportion. And now what we have to do is go over to one prop interval. It's A. One prop Z interval, and that Z signifies that we are talking about the standard normal distribution, because there's another thing, but we're talking about the standard normal, so we're going to choose that. And all you need to use this is the X, the N, and the confidence level. The X is 30. The N is 150. The confidence level is a very common one. It's 90%. I could just put 0.9 if I want. Our p hat, our point estimate was 0.2, which is right in the middle of our confidence interval. 0.2 is dead in the middle. If you add the two endpoints of your confidence interval and divide by 2, if you take the average of these two guys, you will get 0.2. So the answer is, where'd that go? 0.14628, comma, 0.25372. Now, they probably will tell you how much to round. I should have put in 0 too, because that way you can tell where the number is. Let's see what's next. How about we do it using StatCrunch? Same problem, and we can check to see if it's the same. So we just need to get to StatCrunch, which isn't going to be too hard because it says it off to the side. Here's StatCrunch. And we probably could have opened the problem in, oh, no, it doesn't matter. Here we go. Open it again. There's so much clicking. So now the question becomes, where do we go? Well, it should be under Stat, Calc, and then, wait, we're actually trying to do a confidence interval, and it's for the proportion. So let's go to proportion stats. Let's go to one sample, and let's go with the summary. Let's see if this should work. Our successes was 30, our observations was 150, and our confidence level was 0.9. I'm not going to touch anything else. My lower limit is 0.14628. My upper limit is 0.2537. So I can write what I see. It gives me other things. That's the cool thing about StatCrunch. 0.146279 and then 0.25372. It does match the solution that our calculator gave us. Now the only other way to calculate the confidence interval is by hand. First we got to calculate p hat, which is x over n, which is 30 over 150, and that is a fifth, which is equal to 0.2. So it's going to be 0.2 plus or minus the margin of error, which is z sub alpha over 2 times the square root of p times 1 minus p all over n. Now, our 95% confidence means that our alpha is 10%, because confidence level minus 1 is our alpha. And then we have to divide alpha by 2. And here's a picture of what's happening. That 90% is the innermost 90%, which means our alpha is 10%. And, oh, that's combined. which basically means the two tells will make up 5% each for a grand total of 10%. And what we need to do is find this guy right here. So it's inverse norm of everything to the left. Well, to the left, let's shade that region. It's this. Everything to the left. So I'm going to click that and just shade here. The area to the left. Well, that's just going to be 0.95. So if I put in inverse norm of 0.95, it's a very common one. (1.64). So we got 0.2 plus or minus 1.64 times the p, which is 0.2, times 1 minus 0.2 is 0.8, divided by the total number, which is 150. This is 0.2 plus or minus 1.64 times, that's just 0.16 on top. And on the bottom, we got 150. Now it's time to figure this out using our calculator. Well, first I'm just going to do the square root of, let's get out of here. Let's do the square root of point, is that 0.16 divided by 150. And now times by 1.64. My margin of error is 0.053. And I'm going to round it off a little bit more too. So we actually get 0.2 plus or minus it's not going to stay. Move it over here. I have a lot of monitors here, so it's okay. We have 0.53561. So basically what I have to do is add, I'm going to store the last answer. No, this is the last answer. I'm going to store this in X. So I basically had to do 0.2 plus X and 0.2 minus X. And look at what we have here. 0.1464, 0.2535. That matches the other solutions that we got. So finally, we get our, we did it. I don't have to write. You guys see it. And you guys should see all the music. This is being recorded. Well, I stored, so I didn't have to do it that way. I just got lazy. I stored this number into X because I didn't want to have to keep adding it. So like that's, you could do that using the STO button. So this is the button. I just stored it into X. So now it's X. Every time I hit X and hit enter, that's the number. So I had to add it and subtract it from the point estimator. and we got 0.1464, and this, the calculator is the most accurate when you do it by hand. And I also got 0.2535. Hmm. No. Yes. Where did I get what? No, no, don't worry about that. That's fine, Anna, okay? What you have is good enough. It's great. It doesn't have to match mine perfectly. Um, yours is fine. I wouldn't worry about that. Yeah, we might have to double back and check on that. Maybe what you can do is watch this recording and watch what I do it before, because I mean we're gonna move on to the next section, which is slightly different. And then once I'm done with the recording video, I can take some of your questions, okay? We can take it at the very end. How about that? So what we're going to do now is estimate a population mean. And we are going to let's go let's go back to our book real quick. Let's just kind of go over 9.2 really fast. And this is where um see the last problem is. Okay. Yeah, it starts here. So, um, obtain a point estimate for the population mean. So you're going to see how it's slightly different. Um, the point estimate is still good. It's x bar. It's not going to be p hat. It's going to be x bar and then plus or minus the margin of error. Now, the margin of error is going to be the critical number z sub alpha over 2 times the standard deviation divided by the square root of n. So it's actually easier than what we just did. We don't have to do the square root of p times 1 minus p all over n. The standard deviation divided by the square root of n. And then we will have it. We can estimate the mean. Okay, now sometimes they're talking about the student's t-distribution. This is different, all right? This has to do with if we don't know if it's normal or not. So it does get a little bit more technical when we have to bust out with the t-distribution, or they call it the student's distribution. But I will say the method for finding the confidence intervals are pretty much essentially the same stuff. Um, so yeah, I forgot that we will have to consider the t-distribution here in this section. So that does complicate it a little bit. And hopefully you do have the t-interval function on your calculator, because some calculators do not. And if it doesn't, then you're probably going to have to use a table like this table. So we'll get into it. We'll do a couple and see how it goes. So notice that they're using, for their critical value, they're using t sub alpha over 2 instead of z sub alpha over 2. And that, again, that really just depends on what kind of parameters we have. So let's just double check this real quick so that we know what to do when we see it. Let me go back to the original part. Okay. So again, the point estimate thing is all the same. You just take the average of your sample, and that's what we're going to build our confidence interval about the mean. So the next part is here. You have to be aware of the properties for the t-distribution. Okay, yeah, so what they're saying is that, so there's a dilemma. Basically, they're saying that in order to get the margin of error, you would have to know the population deviation. And if you know the population deviation, then you probably know the population mean already. And there's no point in trying to estimate the population mean when you already know it. So we have to assume that we do not know the population standard deviation either when we go to estimate the population mean. It's like we have to assume that we just don't know nothing about the population. We're only working off of a sample. And here they get into well, let's just do, so they're saying, well, we can't use the first one because that's the true population deviation. So why not just use the sample deviation? Here, let me make this a little bigger so you can see this. Oh, not too much. Yeah, that's good. Scoot up. All right. So now they're saying that this would vary too much from sample to sample. This could work for our sample, but all I got to do is use another sample and it's going to be way off again. So what they decided to do was they said, well, forget this mess. Let's just use a t-distribution. And our t-distribution will be our estimation of the population distribution. And this works. It actually works. So the t-distribution is basically, there's a bunch of different normal bell-shaped curves that we can use. And so we use t instead of z. And this is how you would calculate the margin of error. Or the 1t right here. And the thing about t is it uses a degree of freedom. That's nothing. You just subtract 1 from the n, and the calculator will do that for you. So anyway, let's get into it now. Let's just do a couple problems just to get a feel for this. Yeah. So here are the properties. The t-distribution is different for different degrees of freedom. So the bigger the sample, the more accurate the t-distribution will be. The t-distribution is centered at 0 and is symmetric. The area under the curve is 1. And as t increases or decreases without bound, the graph approaches but never equals 0. The area in the tails of the t-distribution is a little greater than the area in the tails of a standard normal distribution. because we are using S as an estimate of little sigma. So yeah, this is good stuff. Good stuff. So there's a table that will enable you to find the critical value. If your alpha is 0.5 or if your alpha over 2 is 0.10 and your degree of freedom is 15, then your critical number is 1.341. But we're going to learn how to calculate this using the calculator. And again, I could go into second distribute right now and do inverse t. And if I put in 0.10 and I put in degree of freedom of 15, I should get what they got. Now, granted, it's negative, but that's easy to fix. But it is negative 1.34, which is what we got. We always have to make it positive, so don't worry about that. That's nothing. So anyway, let's get into this. This is how you would construct a confidence interval. Again, there's some things that have to happen. The sample data must come from an SRS. The sample size is relatively small, 5% or less of the true population, which is pretty easy. The data come from a population that is normally distributed, or the sample size is large. And then a 1 minus alpha times 100% confidence interval for the mu is given by the lower bound, the mean minus this, and the upper bound, the mean plus this, where t sub alpha over 2 is the critical value with n minus 1 degrees of freedom. All right. Well, we can do this by hand, and then we can also use technology, is what the book is saying at this point. All right, let's take a look at some of those practice problems from our course. We'll go into 9.2. Okay, 10 questions. Determine the t-value in each of the cases. Find the t-value such that the area in the right tail is 0.25 with degree 25 degrees of freedom. So we can do this in two ways. We can use the table, or we can use our calculator. We should probably be able to use StackWrench as well. We'll have to look at that. I normally don't do it a bunch of ways. I mean, if I'm doing it, I would use my calculator. So I may not know how to do it using StackWrench, but I'm sure we could figure it out. Like, how hard can it really be, right? So let's make a picture of what they want us to find. Some normal bell-shaped curve. We're dealing with a t-distribution now. So this shape is for degrees of freedom of 25. The shape changes based on the degrees of freedom. The higher the degree of freedom, the more the bell shape will look like a normal bell shape. The smaller the degree of freedom, the more narrow our bell shape will be. So anyway, now what we need to do is find the t-value that corresponds to the right tail being 25%. So let's assume that this region is 0.25. We need to find this guy. What is the z-score, or I should say t-score, that corresponds to the top 0.25? Now, the left, the rest is 0.75. So we're essentially finding the 25th, the 75th percentile. And what we could do is use the table. I'm going to clear the drawing. The table gives the areas are to the right. So we need to go to 0.25. Oh, that's the first column. And now we need to go down to a degree of freedom of 25. Hey, they have it. 0.684. So 0.684 should be the answer. Find the t-value such that the area in the right tail is 0.15 with 8 degrees of freedom. Again, the degree of freedom is the sample size minus 1. So the sample is 9, but we subtract 1 from 9 to get 8 because of that degree of freedom. And it was proven mathematically by doing a degree of freedom, your estimations will come out better. And so here we go. Let's see, where are we? Let's do the technology this time for this one. All right, well, I'm going to go back to inverse t again. That's second, distribute, and then 4. And what it needs is the area to the right. Oh, this is the inverse t. I can't put in the area to the right. I can't put in 115. It's going to be negative. So I have to put in the area to the left, which is 85. Okay? If it's 15 to the right, it's 85 to the left, and my degree of freedom is 8. I got 1.108. And now we're going to try to use StatCrunch to answer the last one. Dun dun dun. Here we go. Here we go. T-stats. Oh, they say T-stats. One sample, and we don't have the data. We have the summary of the data, don't we? And let's make sure. Yeah. Wait a minute. We don't even have that. I think we go into calculator. I think we go into T on our calculator, and this is what we do. The area to degree of freedom is what is that? We don't go into the other thing. We go into a calculator. 28. And then it's the area to the right. Oh no, area to the left, area to the left. So this is tricky. They want 0.2, 0.02, but then they want it to be positive. Let me make sure we did that right. Yeah. 0.508. Wait a yeah, wait. Oh, what's that? Yes. Well, hold on. I'm trying to get. Okay, let me just give me 1 second, okay? I just want to see what went wrong. Maybe I do 98. No? So I have to put in the area first then. 0.298. Yes, 2.154. I didn't like that question. Oh, negative. Isn't it negative, huh? Yeah, I didn't. That question was not that clear. I to be honest. It, but it seems like you got it though. So okay, here's one. Find the critical t-value that corresponds to 90% confidence. So that's 5%. Assume 26 degrees of freedom. So we could just say inverse t of 0.95, and we'll assume 26% degrees of freedom. I got 1.705. 706. Let's get tough. Okay, we're back. Yes. Yes, for the t-value, it's supposed to be positive, but they wanted us to do something different here. I just didn't like that question. Yeah, so here's a picture. One more time. Let me show you. So I just didn't read it carefully either. Um, if they want this piece here, so this piece, they said, make it 0.02. This is a tiny piece. This is 2% of the whole thing. So they want this number. Actually, not Z, I should call it T. They want the T score that corresponds to the lower 0.02. And when I put it into StatCrunch, I wasn't putting it in properly. I should have put in 0.02 but changed the sign around. So like if we go back there and we go back to that, um, we needed to put in the score, leave this blank, the zero point 0.02, and then it's 28. So I need to put in 0.02 when 28 and leave this blank. And that's the answer. Okay. But I don't like that one. That one wasn't that great. Let's move on though. Okay, so this is a question. It says the data from an SRS with 25 observations was used to construct the plots given below. The normal probability plot that was constructed has a correlation coefficient of 0.943. Judge whether a t-interval could be constructed using the data in the sample. Yeah, this is something that we didn't get into. So I think I'm going to remove this question. Um, but I mean, we could try to do it, but this is supposed to be more straight. I believe if it's more straight, then it's more normal. This is skewed. Same thing here. It's skewed to the right, which basically means it has to be it's not good for normality. Um, but again, we just didn't talk about this in this section, so it's just not worth putting on. So I think I'm gonna X this problem out when I get to it. Let's move on. These are good. Construct the 80% confidence interval, the sample size. The sample size is 18, so the degree of freedom will be 17. You have to subtract 1 to get the degree of freedom. You'll need the degree of freedom to get the t critical value, t sub alpha over 2. Because you got to multiply that by the standard deviation divided by the square root of the sample size, which is 18. Maybe we should just do this one. So I'm just going to bring this over. Actually, we could just, let's see, how do we want to do it? Oh, okay. Let's do it in 3 ways. We will do it. I will show you how to do it by hand, by calculator, and by stack crunch. Okay, and then that's going to end our night tonight. So, and I think you'll be able to get through the rest of these. And again, just use your resources. This video will be on YouTube, and hopefully you can use this video to help you. If you're watching it, just speed me up or slow me down or just figure it out. There's tons of resources. There's even other instructors, but I would be careful because sometimes, remember, different stats books will do things differently. Stats is not the same from course to course. It varies quite a lot. So you have to find resources that uses the same material. And oftentimes you can just reach out to me and I can make another customized video based on something, a question that you may have, if I don't answer it directly already. So anyway, let's copy this problem over. Let's get a new page. Paste. Yeah, I guess it's an okay paste. Construct an 80% confidence interval about the population mean if the sample size n is 18. So the first way we're going to do it is by hand. We also need the mean. We need the mean. So we do need to go back to the problem. The mean is 113 and the standard deviation is 10. It also says it's an SRS from a population that is normally distributed. Okay, so the mean is 113 and little s is 10. So what we need to do is find the mean, well, we already know the mean, plus or minus t sub alpha over 2 times S divided by the square root of n. This piece is the margin of error. This piece is what's known as our point estimate. And together is the confidence interval, the entire thing. So that's what we're going to do. But now we have to find T sub alpha over 2. We need to figure out what is that. Now I could use inverse T. Also, I have to know what my alpha is. And since we have an 80% confidence level, my alpha is 20%, which means alpha over 2, the two tells, each tell is 10%. So the right tell has to be 10%, and I'm looking for this T value. And since the sample size is 18, my degree of freedom is 17. And I'm going to use the table since I'm doing it out by hand. Let's really do it out by hand. Keep in mind, the table assumes that you need the area to the right. And our area to the right is 10%. So I'm going to find 10%, which is the fourth column. My degree of freedom was 17. Let me double check that. So the fourth column down to 17. This is easy to remember. 1.333. So we've made some good progress on this problem. My mean is 113 plus or minus 1.333 times S, which was 10, divided by the square root of 18. Now, I have to use technology at this point because 10 over the square root of 18 is too complicated to do. Actually, it's actually not that bad because the square root of 18 can be written as 9 times 2, which can be written as the square root of 9 times the square root of 2, and that's 3 root 2. And I also know that the square root of 2 is 1.41, so we have 3 times 1.41, but you know what? Let's just do 10 divided by the square root of 18. We're getting 2.35, and I'm going to multiply that by 1.333. Wow, look at that. That almost looks like pi. 3.14. Now, we're going to store that value in X. Actually, I'm going to store it in M, which stands for margin of value. So every time I put M, I will get, well, every time I put M, I will get 3.1419. So what we're going to do is add to 113 and subtract from 113. 113 plus M and 113 minus m. And so now I believe that we are done with the confidence interval. We've calculated it out by hand. We got 109.86 comma 116.14. Let's use the calculator to calculate the confidence interval. So clear it out, go to Stat, Test, and this time we're going to do a T interval, number 8. We don't have the data, but we do have the stats. And the stats is the mean is 113, the standard deviation is 10, the sample size was 18, and our confidence level was 80%. (109.86, 116.14). Yes. All right, let's go to StatCrunch and get this answer. And if we can get it in StatCrunch, then we really know how to do it. Okay, so let's just pull up StatCrunch. And I believe we go to, let's just go to T-stats, a sample, summary. The mean was 113, deviation was 10, sample size is 118. Our confidence was 80, and that's it. Our lower limit is 109.857, which can be rounded to 0.86. Our upper limit is 116.14. StatCrunch gave it to us as well. So there it is, our confidence interval in 3 ways. And that is going to wrap up the video. I am going to take any questions that you may have.